Gnanam Paramam Dheyam. Knowledge is supreme.
Now we are discussing finite groups. I also would like to have some examples of the groups which are not finite but our arguments, etc. So I would like to spend some time on explicit examples which are very useful not only in algebra but even analysis courses. And a couple of such groups, before I actually prove the theorem I stated, I want to discuss some examples. Alright, so the examples I want to consider are, for example, the groups. So let me write the groups. These are groups R cross. Of course, this is a group under multiplication, but not only this, if I take the positive ones, so these are precisely the positive real numbers. A real numbers, A non-zero I don't have to write A positive. This is clearly a group under multiplication. This is a subgroup of R cross. Because if I take two positive real numbers, then the multiplication is also positive. The inverse is also positive, and so on. So this is a subgroup of this. So this subgroup, so to understand this subgroup, what is this subgroup? For example, see, when one wants to understand groups, one wants to understand them in terms of the known groups. For example, I want to understand this group in terms of the additive group of real numbers. So in terms of this, so what do we do for that? So let us look at, so let me write the number 1. So let us take any A, which is a real number, positive real number, and it is not equal to 1. We'll see why I am assuming not equal to 1. What is the identity element in this group? 1 is the identity element in this group. Alright. So look at the map. R under addition to R. What is the map? Take any x in the real number and map it to a power x. X is a real number, a is a number which is not 1, and so this is a map. What kind of a map it is this? When you add the numbers and you take the exponential laws will tell you this map is actually a group homomorphism. So this is a group homomorphism to which group now? Let us be more precise. R plus to R dot, and this will never be 0. So it will actually be a map from a non-zero real number inside the non-zero real number. Not only that, this will never be negative. So therefore, it is actually a map from R plus to this group we wanted to study. This is called an exponential map. This is the standard way to convert additive structure to multiplicative structure. And I want to actually check that this map is an isomorphism. This is a group isomorphism. So what do I do? For that I have to give you the map in the other direction. But the map in the other direction is clear. Y goes to log of to the base a y. This is a log to the base a. So these two maps are inverses of each other. So when you want to study this group, it's equivalent to study the real numbers group. And in particular, one wants to study this, one wants to take A equal to E. Then you get the Euler's exponential map. This is a standard exponential map. All right. So that is one thing. Now the same thing if you do it for complex numbers. What do you get? Now I will be little bit brief because I have to save some time. So now if you take the group C plus and the whole multiplicative group C cross dot. Remember there is no positive negative in complex numbers, what we did in real numbers. And there is a natural map here, namely Z going to exponential Z, EXPZ. And then obvious property tells you that this map is a group homomorphism. This is a group homomorphism. So that the standard properties of the exponential that you study in the this is the usual calculus, first calculus course tells you this is a group homomorphism, this is denoted by EXP. Now it is surjective, this EXP is surjective and the kernel is what? Kernel is precisely with kernel is precisely generated, is a subgroup generated by 2 pi I, Z 2 pi I. That is, this is additive subgroup of C plus. So that means that if I go mod the kernel C plus mod this Z 2 pi I, this is isomorphic to C cross multiplicative group. This group is often called a torus group. Okay, more than that I will not say right now. So these are two important groups which will come up in our study sometime. Okay, now third one. Now I want to resume the proof that if G is finite, so proof of what we wanted to prove. We want to prove that if G is a subgroup of K cross, K is any field and the G is finite, then G is cyclic. All right. So, what do we want to prove? G is finite, let us say of order n. Then I want to prove that there is, so to prove that there exists an element G in G with order of G equal to n. This is what we want to prove. All right. So note that if I take, we have noted already that if I take elements of G and their orders, they are divisors of the order of G. This was precisely the Fermat's little theorem. So we know, on the other hand, I want to know if D divides n, D is a divisor of n, then I want to denote this set, all those elements x in G such that order of x is D. this set I want to denote by something. I don't need to denote, I want to denote the cardinality of this set by some, it will depend on this D, so I want to denote it by alpha of D. This is the cardinality. Look, it may happen that this set is empty and there is no element of order alpha D. And our problem is to prove that if I take D equal to n, then alpha of n is non-zero. Non-zero means there is an element of that order. Okay, so what do we know? How many elements are there? What is the bound on alpha D? Alpha D, note that alpha of D is less equal to phi of D, where phi of D is Euler's phi function. This is true for every divisor D of n, where phi of D is Euler's, this is the number of elements m such that GCD of m and D equal to 1 and m is smaller equal to D. So this is called Euler's torsion function. This is the number of elements which are smaller equal to D and of course positive, non-negative, so that the GCD is 1. This is phi of D. And what do we know about this Euler's phi function? The nice formula which I will prove when I introduce group action. So nice formula is, if I take n, this is same as the sum of all phi d's where D divides n. Sum is running over all divisors of n. This is phi d. And how does one prove this formula? This is very easy to prove. Just use this for a cyclic group of order n and then count the number of elements of order D there. They are precisely the GCD, co-prime, etc. So this formula I will take it granted today. On the other hand, if I take any divisor of D and take this alpha D and all, I have exhausted all the elements. So that on the other hand, this n is also same as alpha D, where D divides n. So I have this equality and also I have this. So if all the numbers are strictly smaller than, if all phi d's are strictly smaller than, if alpha d's are strictly smaller than phi d's, then this cannot be equality. Therefore, from this we conclude that you conclude from here that there is an element, there exists an element, there is a divisor, so that alpha D is positive. D is some divisor of n. So that means what? There exists an element A in G with order of A to be D. If the order of D is to be O, alright, so I want to actually prove that, what do we want to prove? Let us analyze what we want to prove. I want to prove that alpha of n is 1. I want to prove, this is what we want to prove. Alright, so if there is some D, so that alpha D is positive and then there is an element of order D, then what happens? Then look at this equation, x power D minus identity, this equation. So in this equation, definitely therefore if I remove or if I look at the subgroup generated by A, this is HA, this subgroup has order D and all other elements of order D are also contained there, because so therefore if I look at this equation on the G minus HA, in this there is no element in G minus H of A of order D. And therefore, what we will conclude that is alpha D equal to phi D, actually for every D. In particular alpha n equal to phi n, which is 1, and therefore there is an element of order. No, I don't. Phi n is definitely non-zero because there are definitely co-prime numbers to n. So therefore alpha n is therefore positive. That means there is an element of order n, and therefore G has an element of order n, and that is what we wanted to prove, that will in particular say that G is cyclic. This proof also I am going to improve. The problem here is I am not using so-called group actions. Once I start using group actions, these proofs will get even improved. Okay, so I will not say much about it, but now I want to prove the theorem that I wanted to prove, that given a prime number P, there is a field with cardinality P power n. Okay, before I do that, so let us say I need a concept of characteristic of a field. Of a field or of a ring. So we have a ring A. A is a ring means we have two operations so that it is a ring, and I will assume usually commutative. So we have this ring and we have additive group. This is a group. And there is an element here. The additive identity is usually denoted by 0. Multiplicative identity is 1. So 1 is an element here. So it makes sense to talk about the order of 1. What is the order of 1? Order of 1 is by definition, you take a subgroup generated by 1. So take H of 1. This is the additive subgroup of A. And if it is finite, the order is the cardinality. If it is infinite, if it is not finite, then the order is 0. This is 0 if this H1 is not finite, and cardinality of H1 if H1 is finite. Let us see what the H1 is. What is H1? H1 is a subgroup generated by 1. Right? That means you have to keep and remember the binary operation is plus. So you have to keep adding 1. So if this was finite, after adding 1 sufficiently many times, it will become 0. So that is the case when this H1 is finite. Never becomes finite means no matter how many times you add 1, you will never get 0. So that means if the order of 1 is either 0 or this set. So what is H1? H1 is precisely subgroup of A generated by 1, but that is precisely Z times order 1. That's what we decided, no? So how many times it will go on? If order 1 is not, this is not finite, it is Z, otherwise it will be some Z mod order. So this is the order. Okay, so what is the characteristic? That is order 1. So that means this order 1 is a kernel. You remember this was the map chi from Z to the ring A, namely any n goes to n times 1. That means n 1 plus 1 plus 1 either 1 n times or minus n times. And the kernel of this is precisely the order. So I am saying something wrong here. So this is not correct. Kernel of this chi is precisely the order of 1. So that means, okay. So that is precisely the characteristic we defined in the earlier way also. In the earlier definition also, it is a generator of the kernel of this chi map. This chi is a unique ring homomorphism, and the generator is called the characteristic, that is order 1. Okay, so now if you have a finite field, so let us take K to be finite field, then this is the finite set, and Z to K, this chi map, this definitely will have a non-zero kernel. If it is kernel is 0, that means this Z sits inside K injectively. So, but that cannot happen. Z is infinite, K is finite. So definitely, because this K is finite, kernel of chi, which is order of 1, this 1 is 1K. This is not 0. This is generated by the order of 1, which is not 0. Therefore, there is a injective map from Z mod, let us call this as some number n. So this Z mod generated by order 1K, this is goes inside K, but K is a field. So therefore this is a subring of the field, which is also integral domain. But it is integral domain and it's finite, because this is non-zero. So this is finite integral domain. Finite integral domains are fields. So therefore this is a field, and therefore this order of K, order of 1K, which is precisely the characteristic of K, which is a prime number. This is P. So this is small p, let us call it. Therefore we have proved that the characteristic of a finite field is always a prime number P. And then we have K here. This is what? This is nothing but Z mod P in the notation. This Z mod P is a subfield of this. This is finite. Therefore, if you think this K as a vector space over Z mod P, the dimension of K as a vector space over Z mod P, if this is some D, then what? Then that will mean that this K is isomorphic to Z mod P vector space of dimension in this is Z power D. That means cardinality of K is precisely cardinality of Zp power D, which is P power D. So therefore what did we prove? We have proved that if K is a finite field, then the cardinality must be power of P. So I will note it what we have proved. So 7. We have proved that cardinality of a finite field, K finite, must be P power some D, where P is some prime number. and in fact that P has to be characteristic of K, which is this P is uniquely determined by K. Now I want to prove the conversely. Conversely, if P is any prime number, and D is any natural number, then there exists a field capital K with cardinality P power D. Okay, so this was first proved by E. H. Moore in 1893. This Moore was a student of Kronecker. And Weierstrass. Actually, Moore was from Chicago, University of Chicago. And those days it was not possible to do PhD in mathematics in America. So they were going to Europe, especially to Germany and France. They were going there to do PhDs. And E. H. Moore was the first mathematician in America who has worked extensively on the fact that to start a PhD program in America. And that was possible in the early 20th century, after the big efforts of Moore. This Moore is the one who proved this theorem. I will continue this proof in the next lecture. So remember, today I only have made a digression on the groups, and ultimately our course revolves around using group theory in theory of equations, solutions of equations. Solutions of equation was much more older than the group theory subject, but nowadays group theory is much more taught than the theory of equations, and I also want to stress more on theory of equations. So we will come back to theory of equation. We will keep coming back and going. This whole course will keep a roller coaster between the group theory and theory of equations. Thank you.